Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electromagnetic waves. So in the previous videos we discussed about starting with the basic introduction to electromagnetic theory, then about the concept of displacement current, which started from a confusion, but Maxwell resolved that confusion and gave us the modified Ampere's law or Ampere-Maxwell law. Then we went on to the basic properties of electromagnetic waves and like that. In this video we are going to discuss about one of the most basic fundamental principles of generation of electromagnetic waves, and we will study it with the help of a very important example, okay, which basically involves a circuit involving two circuit elements, an inductor and a charged capacitor. So how it helps in the generation of electromagnetic waves, that we will see. So we are already aware of we have discussed Faraday's law, okay, Faraday's law of electromagnetic induction, and this is the expression of Faraday's law in vector calculus form, and then Ampere's circuital law, and this is the expression or the modified expression of Ampere's law, which is the Ampere-Maxwell law. And how the basic principle or generation of electromagnetic waves involves change in one field contributing a change in the other. That is, always remember, when it comes to electromagnetic waves, a very simple rule: change in electric field produces a change in magnetic field, change in magnetic field produces a change in electric field. This causes an electromagnetic disturbance, where disturbance in one causes a disturbance in the other, and this results in the generation of an electromagnetic wave in mutually perpendicular planes, also perpendicular to the direction of propagation of the wave. Okay, now is the basic principle of generation of an electromagnetic wave through LC oscillations. That is the topic of this discussion. So basically what this this discussion will involve is we will study a circuit, a very simple circuit consisting of a capacitor and an inductor, capacitor C and inductor L. But there is one thing: this capacitor is initially charged. It can be connected to a voltage source, okay, it is generally connected to a voltage source, okay, so it is charged, okay. Generally it is connected with the help of a switch. When the switch is removed, we get simply a charged capacitor C with all the energy stored in its electrostatic field or electric field. So this is the charged capacitor which is connected to an uncharged inductor, okay, charged capacitor connected to an uncharged inductor. The charge in the capacitor is Q, plus Q on one plate minus Q on the other. So basically what here involves is the capacitor charges and discharges continuously through the inductor. Thereby energy is continuously transferred first from the electrostatic field in the capacitor, then to the magnetic field in the inductor, back then from the magnetic field to electrostatic field, again electrostatic field to magnetic field, like that. This creates a disturbance. First there is a disturbance in the electric field, then there is a disturbance in the magnetic field. A disturbance in electric field, remember, a disturbance in electric field produces a disturbance in magnetic field, again a disturbance in magnetic field produces a disturbance in electric field at a particular point. So this produces electromagnetic waves. And how this happens, let us see. So first is this charged capacitor connected to the inductor. So here the energy in the capacitor, it can be expressed as 1/2 CV square or 1 by 2 Q square by C, where Q is the charge stored in the capacitor and C is the capacitance in farad. And here the inductor is uncharged, inductor L Henry, and at the initial moment all the energy is in the capacitor, in the electrostatic field or electric field of the capacitor. Okay, and we all know the energy stored in the inductor is 1/2 Li square. For capacitor is 1/2 CV square, voltage related. Here it is current related, 1/2 Li square. But here initially the current is 0, so the energy stored in the inductor is 0. Okay, now what happens? The capacitor now starts to discharge through the inductor in this direction. The current flows from the positive to the negative charged plate of the capacitor. Okay, this is the process of discharging of the capacitor in this direction with the current flowing in this direction through the inductor. This is the first stage. Okay, now as this capacitor, this charged capacitor, it discharges slowly, the energy stored in the electric field of the capacitor, it also starts decreasing. Okay, and as per law of conservation of energy, there is no net loss in energy. So the loss of energy or in the electric field or the electrostatic field of the capacitor contributes to a gain in energy in the magnetic field of the inductor. So energy from electrostatic field, 1/2 CV square or 1/2 Q square by C, that is converted into 1/2 Li square, that is energy stored in the magnetic field of the inductor, as by following the law of conservation of energy. So a loss in electric field or a decrease in electric field causes an increase in magnetic field. Decrease in electric field or decrease in electrostatic energy causes an increase in magnetic field or energy stored in the inductor. This is the thing. Now slowly the capacitor discharges fully and the charge in the capacitor becomes 0. Okay, the capacitor fully discharges, the charge on it becomes 0, and the entire energy from the electrostatic field is converted into energy in the magnetic field of the inductor. Okay, energy from the electrostatic field of the capacitor is converted into the energy in the magnetic field of the inductor. Now the entire energy is in the form of this 1/2 Li square. This at this stage when the charge on the capacitor is 0, and here at this stage the energy of the inductor is maximum and the energy of the capacitor is minimum. At the initial stage the energy of the capacitor was maximum and the energy of the inductor was minimum, that is 0. Now what happens? Now as the capacitor is discharged completely, slowly the magnetic field of the inductor, which gradually slowly developed, that will also start to decrease. It will slowly start collapsing. So what will happen? As per Faraday's law of electromagnetic induction and Lenz's law, it will produce a counter EMF. Okay, it will produce a counter EMF. Initially the polarity was like this, flowing from here to here. Now it will produce a counter EMF in the opposite direction, that is this side will become positive and this side, right side, will become positive and left side will become negative after it has discharged. Okay, after this, okay, not during this stage, after this. So it will continue the flow of current in the same direction. This counter EMF across the inductor, okay, here this counter EMF across the inductor, it will cause or it will keep the flow of current in the same direction. So now what happens, this capacitor, it starts charging again, but this time in the opposite direction, because initially if you have marked it, the left plate of the capacitor was initially positive, the right plate was negative, but now because of charging in the opposite direction, the right plate has become positive and the left plate has become negative. So this causes reversal of the voltage, the negative half cycle. Initially it was the positive half cycle, this is the negative half cycle for the electric field, the negative cycle. So now again it starts charging in the opposite direction, okay, because of the counter EMF produced due to Lenz's law, and again the process starts to happen but in the reverse direction. That is, the energy from the magnetic field, it slowly starts decreasing, causing an increase in the energy in the electrostatic field. Slowly this process happens, and again the capacitor is fully charged, okay, the capacitor is fully charged, this one, the capacitor is fully charged but in the opposite direction, okay, the capacitor is fully charged but in the opposite direction. Now after it is fully charged in the opposite direction, it again starts to discharge, okay, it again starts to discharge, but here in this time the current flows in the opposite direction. Initially it was in the if you look at the screen, it was in anti-clockwise direction, now it is in clockwise direction, the current is flowing. Initially it was in anti-clockwise direction, this one, anti-clockwise direction, because left plate was positive, right plate was negative, and current was flowing in the anti-clockwise direction, but in this case the current is flowing in clockwise direction, because in this stage the capacitor is discharging in the opposite direction. So again the same thing happens, the same process, energy from the electrostatic field starts decreasing and in the magnetic field starts increasing. Electrostatic energy decreases, magnetic energy increases, and again the capacitor loses its charge, it becomes zero. Again the energy of the inductor, it becomes maximum. As soon as the capacitor charge becomes zero, the magnetic field starts collapsing, a counter EMF is produced. Here initially during this, it was, this side was positive, this side was negative, but as soon as the magnetic field starts collapsing, the opposite happens, a counter EMF is produced, okay, a counter EMF, again it is produced in the reverse direction, in the opposite direction during the charging of the inductor, and it keeps the current flow in the same direction as previous, and again the capacitor starts to charge. Now this time if you see, it is getting charged in the original polarity, okay, in the original polarity here, this initial polarity. So the same cycle happens again, but now it brings back the capacitor to its initial state. Again the capacitor is fully charged, the energy of the capacitor becomes maximum and the energy of the inductor, it becomes minimum, that is zero. So the capacitor, it returns back to its initial state. So this cycle goes on and on and on. Again the capacitor starts discharging, that gives us the negative half cycle, the decrease in energy and increase in energy of the magnetic field, that gives us the respective positive and negative half cycles of the inductor. So this gives us these waveforms, okay, the electric field, okay, and the magnetic field, the positive and negative half cycles, which basically they signify the charging and discharging of the respective capacitor and inductor, or increase in or decrease in energy of the capacitor. So the positive half cycle represents, increase in energy in one direction. Negative half cycle again represents acquiring of energy but in the opposite direction, reversal of polarity. That is basically that. and whenever there is a change in electric field, it gives us a change in magnetic field. Whenever there is a change in magnetic field, it gives us a change in electric field. This gives us an electromagnetic disturbance in space, which propagates in mutually perpendicular planes and also perpendicular to the direction of propagation of the wave. Okay, so this is the thing. Okay, now the frequency of this oscillations, or the frequency with which the energy gets transferred from one form to another, that is electrostatic energy in capacitor and magnetic energy in the inductor, that is given by F is equal to 1 by 2 pi root over of LC. This is the frequency of oscillations, and this is given by this. The LC oscillations, when the inductor has no resistive component to it. Okay, whenever the inductor has no resistance, attached with it, it has no resistive part, only pure inductor and pure capacitor. In that case, the frequency, the amplitude of the oscillations, they stay the same. Okay, but when, for practical purposes, there is some resistance attached with it, so because of resistance loss in the inductor, because of the resistive part, and the dielectric loss in capacitor, some kind of dielectric loss in the capacitor, the amplitude of the oscillations, it goes on decreasing with time, with increase in time. So this is called as damped oscillations, and this is called as undamped oscillations. This is the ideal behavior. This is the practical behavior. In most practical situations, there will be damped oscillations. The energy of the oscillations, it will decrease. The amplitude of the oscillations, it will decrease. Okay, so now let us just discuss the mathematical analysis of LC oscillations. So here we will discuss the mathematical analysis of LC oscillations. Okay, so basically we'll consider the same circuit. So we have a capacitor and an inductor. Okay, this. So energy is basically continuously converted from one form to another, electrostatic energy to magnetic energy again to electrostatic energy in capacitor, and energy in the magnetic field in the inductor. So here, for the capacitor, okay, for the voltage V is equal to the charge Q, because it gets charged, charge to charge Q, let's say, by the capacitance C of the capacitor, that we all know. So let's say this is the first equation, and then we have the voltage across the inductor. For the inductor, here we are considering the ideal circuit where there is no loss of energy. So the entire voltage from capacitor, it's transformed to the inductor, no loss of energy. Here the same voltage can be represented as minus L di by dt, which is equal to minus N d phi by dt, which is Faraday's law and Lenz's law combined. Okay, Faraday and Lenz's law. So here, this is, let's say, equation number 2. So here, if we compare equations 1 and 2, we will have Q by C is equal to minus L di by dt. That implies L di by dt, where L is inductance, okay, and this is rate of change of current, plus Q by C, that is equal to 0. Okay, this is, let's say, equation number 3. Now we know that current can be written as rate of flow of charge, okay, charge flowing per second. So if we substitute this equation 4 and 3, we will have L d square Q by dt square plus Q by C is equal to 0. This is equation 5. And if we further simplify it, this becomes d square Q by dt square plus Q by LC is equal to 0. This is equation number 6, and this is the form in which we want this equation. Okay, this. Okay, now let us take another example. Okay, so we are slightly deviating to make you understand it. We are slightly deviating from electrical system to mechanical system. We have already covered simple harmonic motion. If you have watched my videos regularly, we have covered simple harmonic motion, SHM. So let us consider a spring mass arrangement. Okay, so where mass M, a block of mass M, is connected to a spring of spring constant K, and this is the equilibrium position equals to 0, and it moves to and fro from this equilibrium position. Okay, plus x minus x, one extreme to the other. So this SHM motion, it can be expressed as d square x by dt square plus k by mx is equal to 0. Here this k by m, it can be used to give the expression for the angular frequency, which is root over of k by m. Okay, this coefficient of x. So this is the angular frequency of SHM motion. So now here, if you compare this equation, let's call it equation number 7, with this equation, equation number 6, d square q by dt square plus q by lc is equal to 0. Here d square x by dt square plus k by mx is equal to 0. So here the coefficient of q and here the coefficient of x. So here k by m is equal to 1 by LC. This is SHM motion. This is LC oscillation. Okay, so that means for the electrical system, okay, the electrical system here, the angular frequency, we can write it as omega is equal to root over of 1 by LC or 1 by root over of LC. Okay, now we know that omega, angular frequency, is equal to 2 pi f. That implies f is equal to omega by 2 pi. That implies f of LC oscillations is equal to 1 by 2 pi root over of LC. This. And this is in radians per second. Okay, this. So this is an interesting analogy between a mechanical system, spring mass arrangement, which is used in simple harmonic motion, and an electrical system. Okay, this, that is a inductor capacitor connected circuit. Okay, so this is how we got the expression for the frequency of LC oscillations, 1 by 2 pi root over of LC. Okay. So here we have discussed the LC oscillations, which is one of the basic concepts related to generation of electromagnetic waves, and we have discussed the working principle and the operating principle, and also derived the frequency of LC oscillations. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.